In this video, we will talk about statically indeterminate systems. First of all, what is a statically indeterminate system? So, if in a system the number of unknowns is higher than the number of available equations, so this system is called statically indeterminate. That means we cannot solve the problem with our basic equilibrium equation. We need additional equations, so we have to write them, well, maybe with the help of displacement relations, which we call compatibility equations. Take an example. Well, we have here a column A, B, C, and it is fixed between two supports, and there is no pre-stress. And in point B, a force P is applied, and in the supports, in order to have an equilibrium, we will have Fa and Fc. So we can write the equilibrium Fa plus Fc minus P equal to 0. That's the only equilibrium relation I can write, but I have two unknowns, so the system is statically indeterminate. I need a second relation. How is this relation? So I can tell that the column length cannot change. So this is fixed, L is constant, whereas due to the tension, LB will increase, and due to the compression, LBC will decrease. So the delta AB, it's the lengthening, and delta BC, their total should be 0. So delta AB minus delta BC, which is shortening, and this is lengthening. So we know that delta is FLAE. So for the two sections, for section 1 and for section 2, I write the delta values, and that is my second equation. Now the problem is solvable, and I can determine Fa and Fc. Another problem. So we have columns 1, 2, 3, all the same length, and we have a rigid plate, and we apply 1000 kilonewtons to this rigid plate, and so we have to determine the stresses in these columns. Well, the first thing I do, I draw a free body diagram of the rigid plate, which is rigid means it will not deform. So F1 plus F2 plus F3 should be equal to 1000, whereas due to the symmetry, F1 and F3 are at the same level, so we call them F. So the equilibrium equation is 1000 minus 2F minus F2 should be 0. Only one equation and two unknown. So the second can be written with a compatibility relation. So if my plate is rigid, when all columns will be shortened, and their shortening delta 1, delta 2, and delta 3 should be equal. Let me write down this relation. I know delta is F, length, the cross section, and the E value. And I know that for steel, E is 200 gigapascals. For aluminum, it's approximately 70 gigapascals. So F length is the same, cross-section changes. Steel has a cross-section of 1000, and that's the elastic modulus of the steel. This is the cross-section of the aluminum column, and that is the modulus of elasticity for aluminum, and that is the force in the middle column. So I do not have to write the third one. Why? Because, well, the first and the third column are identical. As you see, now I have two equations, equation number 1 and equation number 2, and two unknowns, and the problem can be solved. If you solve these two equations, you find that F1 and F3, the steel columns, have a force of 370 kilonewton, and the one in the middle, aluminum column, is taken over a load of 259 kilonewtons. You can take the areas and divide these forces by the areas and find the stresses. Another question. A steel bar is placed between fixed supports so that it just fits. You see, supports upper and lower, length is 1 meter. That is the diameter of the steel bar. It just fits and no pre-stress. So then the temperature is raised from T1. At the beginning, the temperature was 20 degrees, and it is raised to 70 degrees centigrade. Find the average normal terminal stress in the bar. How can I solve it? Okay, there is no external load, so the only thing I can use is the compatibility. We know that the total length cannot change. It will remain 1 meter. Well, if you increase the temperature, well, this length or the bar tries to expand by a value of delta T, but it cannot. Why? Because there will be some support forces acting on the bar, which prevents this bar from lengthening. So the shortening due to these forces, the F, are delta F, and when you write down the delta T, which is the terminal stress, well, if it can expand freely, well, this is the temperature change, this is the length. Alpha is the linear coefficient of thermal expansion. This is when the bar can expand freely, but it cannot expand freely because there will be some compression forces, and these forces will cause a delta F, which will cause a shortening, and this delta F is F times length, the cross section, and E of the bar. So what do I know and what am I looking for? Everything is known. All I need to find is F. F equals to alpha, linear expansion coefficient, temperature change, cross section, and the modulus of elasticity. And take the numerical values, put them in there, and the result is 37.68. Now we know the force divided by the area, pi r square, and the result is 120 megapascals. This is what we call a thermal stress, only due to the change of temperature. Okay, in this video we have discussed indeterminate systems and solved some problems. Thank you for listening.